Hello, this is session 12 and chapter 6, which is imperfection in solids. In this chapter we will talk about solidification mechanisms, different type of defects and imperfections. We will talk about if the number and type of defects can be varied and controlled, and you'll see how do defects affect materials property, and are they undesirable, or there are cases that defects are helping us. As we showed before, when materials start to solidify, the nuclei form. As you can see here, this is the formation of or start of or initiation of nuclei, and then the steps are also shown here. As you can see, start of nuclei, these parts are liquid, and we have crystal growth, and finally the final grain structure, and this is called grain boundaries surrounding each grain. As you can see, this video also shows and talk about different sizes of grain that we can see and how we can observe this grain under microscope. So we see at the end under microscope is a structure like this one, which is resulting from growth of crystals until they meet each other and then fully solidify. Here are links to some very nice videos regarding crystal growth and crystallization and solidification. The first one talks about crystal growth in aluminium and how we can see it under optical microscopy. This is another video talking about crystal solidification. And this one is actually an educational method that was developed in Cambridge about 50 years back, and my students last semester, they made actually a model or way by the help of bubbles to show a structure, to show how or to simulate how a material solidifies, changes from liquid to solid, and then we have group of structure or crystals together and they meet each other at different angles, and then we have grain boundaries. I will show it to you here. Yeah, this video shows, or this method, which is called bubble raft, shows how material crystal structure form and how they behave under tension, compression, so on, so forth. As you can see here, and you can see it in the under this address here. What they need is, as you can see, distilled water filled with glycerin. There is a pump, fish tank pump regulator, a needle, and they try to simulate whatever is happening in during the process of solidification in a real solid material. Here is a glycerin, here is a soap, and then with that they can show different structure, as you can see here. So let's go to the video directly. As you can see, this is very similar to the start of the solidification. You see single crystals are forming at different places of liquid. This is the liquid part, this is single crystal. Each group are progressing and propagating in different angle, and this results finally at different type of defect. As you can see here, we have vacancy, we will talk about it, interstitial, we will talk about it, and grain boundaries. As you can see here, you see this group of excuse me, bubbles or crystals are all aligned this direction. These are aligned in different direction. Whatever you see here is actually is like a border boundary between them. This is very similar to the grain boundary. There are rest. I will show it to you in the later slides. As the materials that have different shapes and types and direction of crystal, they are called polycrystalline. You can see here a schematic shape of polycrystalline material. You can see here grain boundaries, regions between crystals, which is called grain boundaries. In grain boundaries, there is a transition from lattice of one region to that of another region, the neighbor region. Here you see in the boundaries, you see a little bit of disordered, less density in grain boundaries compared to the boundaries themselves. Because there's less density, of course there is high mobility, and there is a fact that some atoms can go inside this region, which is called diffusion, so high diffusivity and high chemical reactivity. If material doesn't have different structure, type of structure is called single crystal. As it was mentioned, crystals or different type of crystal structure are formed after solidification, and this is mainly due to the change of temperature from liquid state to solid state. The grains that you can see, as an example, if you look at this structure which has been polished, you can see grains can be equiaxed like this ones, which means they don't have a preferred orientation, or they can be columnar like these ones, which are elongated in a certain direction, or these are called elongated grains as well. The equiaxes are roughly same size in all directions, like these ones here. An important parameter that affects the shape of these crystals is how they are cooled, and also if they are under any mechanical or cold work. As you can see, we have different colors or different shapes, colors from very white to very black grains. So that's a good question to ask here, why they have different colors. So we'll talk about it in the class. As you can see, because this was a liquid material at very high temperature, and then it lost heat from the border or from the wall, so of course there's a heat flow from the center to the walls, and that's why you see elongated grains along the heat flow or heat direction. This is shown in this video very beautiful. As you can see, walls are where heat is extracted from. You see the molten material and molten metal, and when the process is passing, if we look at this at a microscopic level, you see the first level we have equiaxed or random type of orientation when we have a huge heat transfer, and then we have preferred direction of growth when the rate of cooling is different by the time that we go or reach to the central part of the material or of the molten metal. That's why you see columnar in these areas that have less undercooling, and of course in these shells we have equiaxed grains due to rapid cooling. Here, in order to have a better visibility, grain refiner was added to make smaller, more uniform and equiaxed grains here. Bear in mind that this solidification may result in some disorder and imperfection in this solid. That's why, of course, there is no such a thing as a perfect crystal. But we want to know what are these imperfections that are created during the solidification. We will talk about it. We will talk about the fact that why they are important. Remember that many of the important properties of material are due to the presence of imperfections. But what are the types of imperfection? There are three types of imperfections. The first one is called point defects, and these point defects are includes when we have atom vacancy, when there are some vacant for atoms, when we have interstitial atoms, and when we have substitutional atoms. So we'll talk about this each of them and separate in next slides. The next group is line defects. An example is dislocation, and the other one is area defect, which result in grain boundaries. An example is grain boundaries, and we already talked about grain boundaries. Vacancy is when crystal and atoms solidify, but they leave some vacant area between them. This results in distortion of planes, as you can see in the distortion of the pink lines, which is part of different planes here. If this spaces are occupied by extra atom, or if there is an extra atom sitting in an organized planes of atoms or crystal beside each other, this again results in another type of distortion in the planes, as you can see in the pink lines again, and this is called self-interstitials. In other words, there is extra atom positioned in the atomic sites. To find number of defects, this formula has been proposed, in which NV is number of defects. As you can see, N is the number of potential defect sites, Q is the activation energy, K is the Boltzmann constant, this is the value of K, and T is temperature, of course in Kelvin. The value or the number of potential sites, say if we have, as an example, if we have 36 atoms, each lattice site is a potential vacancy site. So for these 36 atoms, we have 36 atomic potential defect sites. So the value of N for this one going to be 36. The value of QV is either given or can be found from tables. K the same. Temperature is given in the example. So we do a problem, we solve a problem regarding this. Remember that equilibrium concentration varies with temperature, of course. As I said, Q is given, but how it's found is usually found through experiments. If the ratio of NV to N, which is defect concentration, is found in different temperature, of course, by raising the temperature, because the atoms are moving faster, so there is more chance to provide or create more vacant places. So you will see an increase in this ratio by increasing the temperature. And it's found that there is exponential dependence between this ratio and the temperature in degree Kelvin. So if we found the logarithmic value of this ratio in terms of 1 over t, then of course the slope of this line gonna be, based on this relation, gonna be QV divided by K. The Boltzmann constant is known, of course, and then from here they can find the value of QV, which is activation energy. Okay, here is an example. We want to estimate the vacancy concentration and find the equilibrium number of vacancies in 1 meter cube of copper at 1000 degrees Celsius. So because it's copper, we go to the very first page of the book and we look for its physical and some chemical properties. As an example, density of this material is 8.4 for this temperature. Of course at room temperature it's a larger value, as you can see in the table is 8.94. The atomic weight in gram per mole for copper is 63.5. QV is found from experiment and is given in the question as this value, 0.9 electron volt per atom, and this means activation energy for each atom is 0.9 electron volt, and Avogadro's number, is this value. Using the formula that was given in the previous slide, so we have NV divided by N is equal to exponential of QV divided by K and T. T in degrees Celsius is 1000, so in degree Kelvin is 1273. Boltzmann constant is this value. QV is substituted from the value that's given, and these numbers, the ratio of the vacancy is equal to 2.7 times 10 to minus 4. So this is the ratio of vacancy number of vacancy divided by the available atomic space or potential atomic sites. This picture, this electron microscope view of surface of nickel aluminium, 110 surface of nickel aluminium. Here shows vacancy concentration. Of course, by increasing temperature, surface island, these islands here of atoms will grow. Why? Because the equilibrium vacancy concentration increase with atom motion from the crystal to the surface where they join the island. As you can see here this island and this top surface grows or shrink to maintain the vacancy concentration in the bulk. If you look at the point defects in ceramics, we see vacancies exist in ceramic for both cation and anion, as you can see here. This is anion vacancy and this one is cation vacancy. Cation is the blue atoms and anion is the orange one. And regarding interstitials, interstitials exist for cations, as you can see here. They are normally observed for anions because anions are large relative. They are not observed actually because they are large relative to the interstitial sites. These guys are larger than to make interstitial, so this is very common for cation in ceramics. If in ceramics there is a pair of cation interstitial cation vacancy, it's called Frankel defect, and if there is a pair set of cation and anion vacancies, it's called Schottky defect. Here, similar to the formula that we talked, equilibrium concentration of defects is relevant to this ratio here. If we look at imperfections in metals, there are two outcomes if impurity B in orange added to host A in gray. The first one is substitutional or solid solution of B in A, which result in random distribution of a point defect as shown here. Or you see interstitial solid solution of B inside A. This is found usually in steel as carbon in iron, and this is the solid solution of copper in nickel. This schematic also shows a solid solution of atom B in A plus particles of a new phase. Usually this is happening for a larger amount of atom B. The new phase that you see here has a different composition and sometimes a different structure. When does this solid solution usually happen? Based on W. Hume-Rothery rule, a group of requirements are required so that the solid solution in metals happening. The first one is the atomic radius. If the atomic radius is less than the change in the differences in the atomic radius is less than 15%. The second condition is proximity in periodic table. As an example, those materials or those metals that have similar electronegativities. Third condition is same crystal structure for pure metals. And the fourth one is valency. Here metals will have a great tendency to dissolve a metal of higher valency than one of the lower valency. So if all these conditions are available and are happening, are valid, then you would see solid solution in the metal. Here we can see the application of Hume-Rothery rules for solid solution. Say for example we want to know we want to predict which one, aluminium or zinc, or silver to dissolve in zinc. So we look at their crystal structure, aluminium and silver. They have the same type of crystal structure. Zinc has a different one. Their electronegativity is 1.6 is 1.9 and this one is 1.5. So aluminium is more probable to dissolve in zinc than silver. And you see this one so we can predict aluminium will dissolve in zinc due to closer value of electronegativity. For this one, zinc or aluminium, which one is going to be dissolved in copper? Again, you see zinc is HCP, aluminium FCC, and copper is FCC. So due to having similar crystal structure, so aluminium is predicted to dissolve in copper. So this is for the 12th session, and we continue the rest about imperfection polymers in the next session. Thank you.